An evolutionarily stable strategy is a strategy which, if adopted by a population in a given environment, cannot be invaded by any alternative strategy that is initially rare. It is relevant in game theory, behavioral ecology, and evolutionary psychology. An S is an equilibrium refinement of the Nash equilibrium. It is a Nash equilibrium that is evolutionarily stable. Once it is fixed in a population, natural selection alone is sufficient to prevent alternative strategies from invading successfully. The theory is not intended to deal with the possibility of gross external changes to the environment that bring new selective forces to bear. First published as a specific term in the 1972 book by John Maynard Smith, the S is widely used in behavioral ecology and economics, and has been used in anthropology, evolutionary psychology, philosophy, and political science. History. Evolutionarily stable strategies were defined and introduced by John Maynard Smith and George R. Price in a 1973 Nature paper. Such was the time taken in peer-reviewing the paper for Nature that this was preceded by a 1972 essay by Maynard Smith in a book of essays titled On Evolution. The 1972 essay is sometimes cited instead of the 1973 paper, but university libraries are much more likely to have copies of Nature. Papers in Nature are usually short. In 1974, Maynard Smith published a longer paper in the Journal of Theoretical Biology. Maynard Smith explains further in his 1982 book Evolution and the Theory of Games. Sometimes these are cited instead. In fact, the S has become so central to game theory that often no citation is given, as the reader is assumed to be familiar with it. Maynard Smith mathematically formalized a verbal argument made by Price, which he read while peer-reviewing Price's paper. When Maynard Smith realized that the somewhat disorganized Price was not ready to revise his article for publication, he offered to add Price as co-author. The concept was derived from R. H. MacArthur and W. D. Hamilton's work on sex ratios, derived from Fisher's principle, especially Hamilton's concept of an unbeatable strategy. Maynard Smith was jointly awarded the 1999 Crawford Prize for his development of the concept of evolutionarily stable strategies and the application of game theory to the evolution of behavior. Uses of S. The S was a major element used to analyze evolution in Richard Dawkins' best-selling 1976 book The Selfish Gene. The S was first used in the social sciences by Robert Axelrod in his 1984 book The Evolution of Cooperation. Since then, it has been widely used in the social sciences, including anthropology, economics, philosophy, and political science. In the social sciences, the primary interest is not in an S as the end of biological evolution, but as an end point in cultural evolution or individual learning. In evolutionary psychology, S is used primarily as a model for human biological evolution. Motivation. The Nash equilibrium is the traditional solution concept in game theory. It depends on the cognitive abilities of the players. It is assumed that players are aware of the structure of the game and consciously try to predict the moves of their opponents and to maximize their own payoffs. In addition, it is presumed that all the players know this. These assumptions are then used to explain why players choose Nash equilibrium strategies. Evolutionarily stable strategies are motivated entirely differently. Here, it is presumed that the player's strategies are biologically encoded and heritable. Individuals have no control over their strategy and need not be aware of the game. They reproduce and are subject to the forces of natural selection. It is imagined that alternative strategies of the game occasionally occur, via a process like mutation. To be an S, a strategy must be resistant to these alternatives. Given the radically different motivating assumptions, it may come as a surprise that S's and Nash equilibria often coincide. In fact, every S corresponds to a Nash equilibrium, but some Nash equilibria are not S's. Nash equilibria and S An S is a refined or modified form of a Nash equilibrium. In a Nash equilibrium, if all players adopt their respective parts, no player can benefit by switching to any alternative strategy. In a two-player game, it is a strategy pair. Let E represent the payoff for playing strategy S against strategy T. The strategy pair is a Nash equilibrium in a two-player game if and only if this is true for both players and for all Ts. In this definition, strategy T can be a neutral alternative to S. A Nash equilibrium is presumed to be stable even if D scores equally, on the assumption that there is no long-term incentive for players to adopt T instead of S. This fact represents the point of departure of the S. Maynard, Smith and Price specify two conditions for a strategy S to be an S. For all Ts, either E greater than E, or E equals E and E greater than E. The first condition is sometimes called a strict Nash equilibrium. The second is sometimes called Maynard-Smith's second condition. The second condition means that although strategy T is neutral with respect to the payoff against strategy S, the population of players who continue to play strategy S has an advantage when playing against T. There is also an alternative, stronger definition of S due to Thomas. This places a different emphasis on the role of the Nash equilibrium concept and the S concept. Following the terminology given in the first definition above, this definition requires that for all Ts E and E greater than E. In this formulation, the first condition specifies that the strategy is a Nash equilibrium, and the second specifies that Maynard-Smith's second condition is met. Note that the two definitions are not precisely equivalent. For example, each pure strategy in the coordination game below is an S by the first definition but not the second. In words, this definition looks like this. The payoff of the first player when both players play strategy S is higher than the payoff of the first player when he changes to another strategy T, and the second player keeps his strategy S. And the payoff of the first player when only his opponent changes his strategy to T is higher than his payoff in case that both the players change their strategies to T. This formulation more clearly highlights the role of the Nash equilibrium condition in the S. It also allows for a natural definition of related concepts such as a weak S or an evolutionarily stable set. Examples of differences between Nash equilibria and S's in most simple games. The S's and Nash equilibria coincide perfectly. For instance, in The Prisoner's Dilemma there is only one Nash equilibrium, and its strategy is also an S. Some games may have Nash equilibria that are not S's. For example, in Harm Thy Neighbor both are a Nash equilibria, since players cannot do better by switching away from either. However, only B is an S. A is not an S, so B can neutrally invade a population of A strategists and predominate, because B scores higher against B than A does against B. This dynamic is captured by Maynard-Smith's second condition, since E equals E, but it is not the case that E greater than E. Nash equilibria with equally scoring alternatives can be S's. For example, in the game Harm Everyone, C is an S because it satisfies Maynard-Smith's second condition. D strategists may temporarily invade a population of C strategists by scoring equally well against C, but they pay a price when they begin to play against each other. C scores better against D than does D. So here, although E equals E, it is also the case that E greater than E. As a result, C is an S. Even if a game has pure strategy Nash equilibria, it might be that none of those pure strategies are S. Consider the game a chicken. There are two pure strategy Nash equilibria in this game. However, in the absence of an uncorrelated asymmetry, neither swerve nor stay are S's. There is a third Nash equilibrium, a mixed strategy which is an S for this game. This last example points to an important difference between Nash equilibria and S. Nash equilibria are defined on strategy sets, while S are defined in terms of strategies themselves. The equilibria defined by S must always be symmetric, and thus have fewer equilibrium points. S versus evolutionarily stable state. In population biology, the two concepts of an evolutionarily stable strategy and an evolutionarily stable state are closely linked but describe different situations. In an evolutionarily stable strategy, if all the members of a population adopt it, no mutant strategy can invade. Once virtually all members of the population use this strategy, there is no rational alternative. S is a part of classical game theory. In an evolutionarily stable state, a population's genetic composition will be restored by selection after a disturbance, if the disturbance is not too large. An evolutionarily stable state is a dynamic property of a population that returns to using a strategy, or mix of strategies, if it is perturbed from that initial state. It is part of population genetics, dynamical system, or evolutionary game theory. Thomas applies the term S to an individual strategy which may be mixed, and evolutionarily stable population state to a population mixture of pure strategies which may be formally equivalent to the mixed S. Whether a population is evolutionarily stable does not relate to its genetic diversity. It can be genetically monomorphic or polymorphic. Stochastic S. In the classic definition of an S, no mutant strategy can invade. In finite populations, any mutant could in principle invade, albeit at low probability, implying that no S can exist. In a finite population, an S can instead be defined as a strategy which, should it become invaded by a new mutant strategy with probability p, would be able to counter-invade from a single starting individual with probability greater than p. Prisoner's dilemma and S. A common model of altruism and social cooperation is the prisoner's dilemma. Here a group of players would collectively be better off if they could play cooperate. But since defect fares better, each individual player has an incentive to play defect. One solution to this problem is to introduce the possibility of retaliation by having individuals play the game repeatedly against the same player. In the so-called iterated prisoner's dilemma, the same two individuals play the prisoner's dilemma over and over. While the prisoner's dilemma has only two strategies, the iterated prisoner's dilemma has a huge number of possible strategies. Since an individual can have different contingency plan for each history and the game may be repeated an indefinite number of times, there may in fact be an infinite number of such contingency plans. Three simple contingency plans which have received substantial attention are always defect, always cooperate, and tit for tat. The first two strategies do the same thing regardless of the other player's actions, while the later responds on the next round by doing what was done to it on the previous round. It responds to cooperate with cooperate and defect with defect. If the entire population plays tit for tat and a mutant arises who plays always defect, tit for tat will outperform always defect. If the population of the mutant becomes too large, the percentage of the mutant will be kept small. Tit for tat is therefore an S with respect to only these two strategies. On the other hand, an island of always defect players will be stable against the invasion of a few tit for tat players, but not against a large number of them. If we introduce always cooperate, a population of tit for tat is no longer an S. Since a population of tit for tat players always cooperates, the strategy always cooperate behaves identically in this population. As a result, a mutant who plays always cooperate will not be eliminated. However, even though a population of always cooperate and tit for tat can coexist, if there is a small percentage of the population that is always defect, the selective pressure is against always cooperate, and in favor of tit for tat. This is due to the lower payoffs of cooperating than those of defecting in case the opponent defects. This demonstrates the difficulties in applying the formal definition of an S to games with large strategy spaces, and has motivated some to consider alternatives. S and human behavior. The fields of sociobiology and evolutionary psychology attempt to explain animal and human behavior and social structures. largely in terms of evolutionarily stable strategies. Sociopathy may be a result of a combination of two such strategies. Evolutionarily stable strategies were originally considered for biological evolution, but they can apply to other contexts. In fact, there are stable states for a large class of adaptive dynamics. As a result, they can be used to explain human behaviors that lack any genetic influences.